Welcome you all in the lecture number 18 of Abstract Algebra MTL 6051. In this lecture we will going to discuss commutator group. What is commutator? Number 2, solvable group. Properties of commutator. And theorem related to commutator. Theorem related to commutator and solvable group. Okay. So first let us see what is commutator. Okay. If G be a group and AB is any element of G, right? If AB belong to G, then consider element of the type A, B, A inverse, B inverse, or A inverse, B inverse, AB. Either this type of element or this type of element. AB, A inverse, B inverse, A inverse, B inverse, AB. What is this or this? This is nothing but commutator of A and B. Okay, and this commutator is denoted by this, right? AB, bracket AB. Let us consider capital S. What is capital S? Set of all such type of element. Which type of element? This type of element. Let capital S be set of all commutator in G, and the subgroup generated by capital S be the set of all commutator, and the subgroup generated by S is denoted by G prime. Okay, then G prime is known as commutator subgroup of G and denoted by G prime is equal to bracket GG dash. Right? What is capital S? Capital S is set of all commutator. This capital S is set of all commutator. Means capital S is element of this type. AB, A inverse, B inverse, where AB belong to G. S is this type, and this G dash is generated by S. What is G dash? G dash is generated by S. Okay. Then this G dash is known as commutator subgroup, right? And denoted by G dash or G prime, whatever you call it, or G dash or G prime, is denoted by bracket GG. Now let us see theorem related to this commutator. If G prime is commutator subgroup, what is G prime? G prime is commutator subgroup of group G. Then G prime is normal. If G prime is commutator subgroup, then G prime is normal. For this we have to show that X element of G prime, X inverse, belongs to G prime for all X belong to G. What is this? This is element of G prime. Okay. Which type of element G prime have? G prime has element of type bracket AB belong to G. What is bracket AB? This AB, A inverse, B inverse. Okay. This type of element. Then we have to show that X AB, X inverse belongs to G prime. Okay. This is true for all X belong to G. If we are able to prove this, then G prime is normal subgroup of G. Okay. So first thing is G prime is normal in G, and second, if G prime is normal, then the quotient group we can define G by G prime. If G prime is normal, then this quotient group exists. Then this G by G prime is abelian. Okay. And third property says that G prime is smallest subgroup of G. Right? This G prime is smallest, not subgroup, in fact normal subgroup of G, smallest normal subgroup of G. Okay, let us see proof first. What we have to show? We have to show that G prime is normal in G, right? We already discussed how we will prove G prime is normal. For this we have to prove that X AB bracket AB X inverse belong to G prime for all X belong to G. See, what is GG? This is commutator subgroup and it is generated by commutator. And what is commutator? Commutator is of the form bracket GH. What is G and H? Belong to capital G, right? Then we have to show that G prime is normal subgroup of G, right? For this we have to prove this. Okay, so let us see what is GH. See, what is bracket GH? Bracket GH is equal to G H G inverse H inverse. Okay, then what is GH inverse? This GH inverse is GH G inverse H inverse whole inverse. What is this? This is H in apply reversal rule. H inverse inverse H, G inverse inverse G, H inverse G inverse. And what is this? This is HG. Okay, so GH inverse is HG. It means inverse of a commutator is commutator. Inverse of commutator is again commutator. Okay, so inverse of commutator is commutator. Okay, this thing GH inverse is equal to this CHG. Okay, now consider this conjugate element EX GH X inverse. EX, what is GH? Bracket GH. Bracket GH is GH G inverse H inverse. Now this we can write it as follows: X G X inverse X H X inverse. Why? Since this X inverse and X, this become identity, right? This become identity. Okay, so no problem. This can be written in this form. Okay, in this form X G X inverse X H X inverse X G inverse X inverse X H inverse X inverse. Okay, and what is this? This is nothing but the commutator. What is this? X G X inverse X H X inverse. Why? See, X G X inverse X H X inverse. Then inverse of first element X G X inverse whole inverse and X H X inverse whole inverse, right? First element is C. What is first element? So, see, first thing is C and second one is this. And what is this? This is nothing but this thing. Apply reversal rule. X inverse inverse, that is X. G inverse, right? And X inverse, this thing. And apply reversal rule here. X H inverse X inverse. Okay, so this is nothing but X G X inverse X H X inverse, commutator of this. Okay, now consider product of commutator G1 H1 bracket G1 H1 bracket G2 H2 bracket GK HK belong to G prime, right? Then X inverse. This again we write in similar way: X commutator bracket G1 H1 X inverse, then X G2 H2 X inverse, since this is identity, right? Dot so on. this becomes again element of G prime, since this is element of G prime, this is element of G prime, this is element of G prime, and since G prime is subgroup, so their composition is also element of G prime. So G prime is normal subgroup of G. What is G prime? That is GG. It means G prime is normal subgroup of G. Okay. The first result is proved. What is the second result? Then G by G prime is abelian. We have to show that this thing. This is abelian. What is the condition of abelian? If group G is abelian, then AB is equal to BA, right? What we have to prove that? We have to prove that G by G prime is abelian. Right? We have to prove that G by G prime is abelian. So consider its two elements. One is small g capital G prime, small h capital G prime. If we are able to prove G prime, H prime equal to H prime G prime, right? If we are able to prove this, right, then this result is none. Then G by G prime is abelian. How we will prove? Let us simplify it more. G prime and H prime. What is inverse of this? G inverse G prime. What is inverse of this? H inverse G prime. Okay. So let us consider. Right. G prime H prime. What is G prime H prime? G prime H prime is G prime H prime and inverse of first one, that is, what is inverse of G prime, right? That this is equal to G inverse G prime. Why? Since in coset AH inverse, what is this? This is A inverse H. Okay. So what is this? This is element of G by G prime. That is, this is nothing but a coset. So inverse of coset is equal to inverse of element into G prime. Okay, just like this one. So G prime, H prime, and inverse of first one, G inverse G prime, H inverse G prime. Okay. Now, what is the product of two coset? AH BH is equal to ABH, right? Then apply this property here. This is AH BH CH DH, right? This type of element. Then this is equal to ABCD, right? ABCD means GH G inverse H inverse G prime. Okay. Since AH BH CH DH is equal to ABCDH, so GH G inverse H inverse G prime. Okay. And what is GH G inverse H inverse? That is GH G prime. Okay. What is GH? GH is element of G prime. And we know that if A belongs to H, then what is AH? AH is nothing but H. Similarly, what is bracket GH? Bracket GH is element of G prime. So what is this coset? This coset is nothing but G prime. Okay. It means, what is this? This is nothing but G prime. Right. It means G prime, H G prime, G inverse G prime, H inverse G prime equal to G prime. Okay, since this is identity, and consider these two elements right hand side, then G prime H prime equal to H prime G prime. Okay, this is the property of commutativity. Hence this result hold for all element of G by G prime. Hence G by G prime is abelian. Okay. Now come to the third part. we have to show that G prime is the smallest normal subgroup of G. Okay. So if we prove that G prime is the smallest normal, let us consider one more normal subgroup. Let N is normal subgroup of G. Okay. Okay. If N is normal subgroup and G by N is abelian, N is normal subgroup and G by N is abelian. Okay. Then Gn Hn is equal to what? Hn Gn, or this thing you can write as Gn Hn G inverse N H inverse N. Okay, and this thing can be written as GH G inverse H inverse capital N. See here, Gn Hn is equal to Hn Gn. Why? Since G by N is abelian. So this thing can be written as in this way, right? And what is this? This is equal to identity. And what is identity of G by N? That is N. Okay, so N is equal to this one. So GH G inverse H inverse N. What is this? This is bracket GH N. Okay, GH N is equal to N. It means what? AH is equal to H means AH is equal to H means A belongs to capital H. Similarly, bracket GH N equal to N means bracket GH belong to capital N. What is bracket GN? GH. Bracket GH is element of commutator group. What is commutator group? G dash. So element of this type GH, which is the element of G prime, is always element of capital N. What is capital N? Capital N is any arbitrary normal subgroup, right? So capital N is any arbitrary normal subgroup which containing all the element of commutator group. Hence, commutator group, that is G prime, is smallest normal subgroup, right? Therefore, G prime is less than capital. Okay. Now, fourth part you have to prove that. But before going to fourth part, we have to prove Abelianization. Okay. Now see, universal property of Abelianization. What is universal property of Abelianization? If phi is homomorphism, okay, then there exists phi bar from G by G prime to A. And what is phi? Phi is the composition of phi bar and pi. What is pi? Pi is natural homomorphism, right? It means what is phi? G by G prime to A. This is phi, and from G to A. Then this is pi G by G prime. Okay, and from G by G prime to A, this is phi bar. It means phi bar of pi is equal to phi. Okay, what is phi bar? Phi bar is G by G prime to A, and what is pi? Pi is natural homomorphism from G to G by G prime. Okay, this is universal property of abelianization. And what is the proof? What is phi? Phi is this. Okay, then what is kernel of phi? This is G, this is A, and this one is phi. What is kernel? This thing is kernel. Okay, this thing is kernel. What is this? Kernel of phi. Kernel of phi is normal subgroup of G. Let us call this kernel of phi capital. This is normal subgroup of G. Okay, so call this kernel phi is capital N. Then what is G prime? G prime is smallest normal subgroup. So this G prime is smallest normal subgroup of this one. Now this phi bar is a map from G by G prime to A, and define this. What is the element of G by G prime? This is the element of small g capital G. And what is this? This is phi of G. So this phi bar defined in this way. Then we have to prove that this phi bar is well defined. This is homomorphism. Okay, let us see. Consider two elements are equal. Small g capital G prime equal to h G prime. Then what is this? This is equal to G H inverse belong to G prime, right? Then G H inverse belong to G prime means phi G H inverse. What is phi G H inverse? Is I, right? Why? What is phi G inverse? Since phi is homomorphism, therefore phi G phi H inverse and phi G phi H. Okay. What is phi G? This is phi bar small g capital G prime. And what is phi H? Phi bar H G prime. Okay. It means if elements are equal, then their images are equal. Okay. So this phi bar is well defined. First thing is, okay, phi bar is well defined map. Okay. Now next, phi bar is homomorphism. Then phi bar G G prime H G prime is equal to phi of GH, right? Phi of GH. This thing equal to phi bar GH capital G prime, and this is equal to phi GH. And what is phi GH? This is phi G and phi H. Okay. And this is, what is phi G? Phi bar G G prime. What is phi H? Phi bar H G prime. Okay. This thing. So phi is equal to phi bar, composition of phi bar and pi. Okay. Now see one another group. What is solvable group? A group G is said to be solvable. Is said to be solvable if there exists sequence of subgroup in the form this H0, H1, H2, Hn. That is Hn is G and H0 is E, right? In between there exists a sequence of subgroup H1, H2, Hn minus 1 such that each Hi is normal subgroup of Hi plus 1, and this factor group Hi plus 1 upon Hi is abelian. Okay, this condition is distinct. No? This is abelian. This factor group is abelian group. If a series exists of this type, then this is known as solvable series. Okay.